Effective utilization of reclaimed asphalt pavement by using Rejuvenator in stone mastic asphalt for binder course. Abstract road construction crossing the world created huge demand for construction materials. Natural aggregates is the prime material for the road construction. Use of aggregates leads to question about the preservation of natural resource. In other hand, use of recycled pavement asphalt, RAP, as an alternative material in place natural aggregate which makes environmental friendly construction material. This research investigated the feasibility of using reclaimed asphalt pavement in stone mastic asphalt mix by modifying the binder with waste engine oil and elastomer modifier. RAP is replaced with aggregates at 10%, 20%, 30%, and 40%. Further, in order to increase the percentage of RAP in SMA mix, waste engine oil is added to binder course, i.e., RAP of 50%, 60%, and 70%. The results indicated that 60% of RAP is found to be feasible through laboratory investigation for SMA mixes and 70% RAP is found to be feasible to use in SMA mix through laboratory investigation by modifying binder with waste engine oil. Keywords: RAP, bituminous mix, waste engine oil, fatigue, rutting. Introduction. The India road network evolved tremendously in 5 decades to become the main transportation system in the country. India is the second largest country by area in terms of geographical area, 32 million square km, and it takes 4th place in world in terms of motor vehicle, 3.8 million. But it has very small paved roads with respect to overall area, which in turn leads to increase in transportation cost in the world market. With more number of vehicles or traffic volume and load of vehicle on the pavement, it becomes very important to provide a pavement meeting the required standards. In order construct the road highly durable, safe, with good riding comfort. By using high durable asphalt mixtures which will help in reducing the vehicle operation cost and maintenance cost, pavement service life. In developing countries, above mentioned parameters becomes very important to use durable asphalt mixture in the surface layer, e.g., SMA, Vale ETAL 2006. These SMA mixtures are gap-graded mixes with high structural and functional performance. They are discontinuous gradations with higher coarse aggregates of about 70 to 80% by weight to give stone-to-stone contact, skeleton-like structure, of high stability with high binder content of about 6 to 7% and air voids approximately 4%, it requires the addition of fibers of about 0.3% of weight of the mix to prevent the drain down through the air voids. This research aims to determine the feasibility of using reclaimed asphalt pavement in SMA mix, due to more percentage of RAP materials available in the southern part of India. RAP material constitute the potential alternative material to natural aggregates. To evaluate the performance characteristics of SMA mix with elastomer modifier, following tests have been carried such as Marshall stability, indirect tensile strength, rutting, fatigue, drain down and moisture susceptibility. The obtained test results are compared with conventional SMA mix with RSP and SMA mix with RAP and elastomer modifier. Background. Stone mastic asphalt, SMA, was first used by Germans in 1960s as a mix would resist the wear and tear of studded tire. Main advantages of SMA were found to be improved low temperature performance, highly rut resist, reduced noise of tires and increased service life, Cooley and Hurley 2004. Due to its successful performance in Germany, the mix started to use in different part of the world like USA, Spain, France, and North America. SMA application has been carried mainly on the high-volume roads as a high-resistance and high-durable layer which helps in noise reduction and light reflection during rainy season. A typical SMA mix consists 70% of coarse aggregates on or above 2.36 mm sieve, filler in SMA is about 10% of weight of mix passing on 0.075 mm sieve, Dong and Tan 2011. Cellulose fiber of about 0.3% of weight is added to prevent drain down. If fibers are not added to the mix, it will leads formation of fat patch on the pavement surface. Michael et al. 2003, Stone-on-stone contact formed in the mix makes the more rut-resist and highly durable mixture. Stabilizer additive, fibers are added due to high binder content, drain down of bitumen from SMA mix during production, transport, and laying of the mix occurs. Hence, in order to prevent the drain down, fibers are added which may be organic or inorganic or mineral materials. Fibers such as coconut coir, glass, minerals, and cellulose fibers, only pelletized, can be utilized. Navis Fio ETAL 2004. Addition of fibers should not exceed more than 0.3% by weight of the mix. Mix is designed as per ASTM D6390. Length of fiber is about 8 mm, ash content is max 20% non-volatile, oil absorption is 4 times more than the fiber weight, and moisture content should be less than 5% than by weight of the fiber. Many researchers have shown that SMA mix design been developed by Marshall Mix Design Method, Muniandi and Huat 2006, by adopting Marshall method of mix design. Performance results such as dynamic stability, fatigue life, and water sensitivity of SMA mix is evaluated. In the present research studies, RAP is replaced with natural aggregated by adopting Marshall mix design to evaluate the performance characteristics of SMA mix. Materials: aggregates and filler. In the present study for the design and production, SMA mix, granite, and dust of rock was used, with baghouse dust as a filler. The natural aggregates were procured from KMS Crusher, Bangalore, Karnataka, India. Filler material used in the research is baghouse, which is the final product obtained by washing stone dust during production of sand. Baghouse for the research is provided by Sri Venkateshwara Crushes, Bangalore, Karnataka, India. Fibers. Most commonly used fiber in SMA mix is cellulose, which are physiologically and toxicologically safe, and they are purely natural cellulose resources, Bose ETAL 2006. Small amount of about 0.3% is added to the mix to prevent drain down of asphalt and to increase stability and durability of the mix. Cellulose fiber used in the present research is provided by Smart Technology, Pune, Bangalore, Karnataka, India. And Table 3 shows the properties of fiber which is used for the SMA mix. Reclaimed asphalt pavement. Reclaimed asphalt pavement are the materials derived from reprocessed pavement which contains asphalt and aggregates. The derived materials are subjected to crushing and screening to obtain RAP of well-graded aggregates coated with bitumen. Recycling of existing asphalt pavements allows the industry to produce new pavements with effective utilization of material and energy, making it cost-effective. 7. For this study, RAP is procured from Chittor district, where some part of Bengaluru Tirupati Highway, NH206, was scarified for construction of cement concrete pavement. Bitumen, CRMB 55. Binder content required for the SMA mix is higher when compared to other bituminous mixes. In this study's crumb rubber modified bitumen of grade 55, CRMB 55, is used. CRMB was procured from the MD Constructions, Rajajanagar, Bengaluru. Procured bitumen is tested for penetration, softening point, flash point, elastic recovery, and results obtained should meet the required specifications as per IRC-SP 53:2010. In the present research work, Bahu's dust is used as mineral filler in SMA mix. Bahu's mineral filler used for the study was obtained from SLV Crushers, Periyapatna, and Karnataka. The gradation is carried out as per MORTH Table 500-36. Waste engine oil, WEO. Reclaimed asphalt pavement, RAP, consists of aggregates coated with the bitumen content. The coated binder will be of aged one and its properties are not as good as original binder. The aged binder present in RAP will be lack in oily compounds and doesn't behave as fresh bitumen. In the present study, waste engine oil is used as a rejuvenators and which was procured from the motorcycle garage Bengaluru. Marshall mix design. Once the gradation is fixed, Marshall method is used to determine the OBC, optimum binder content, in SMA mix. The SMA mix will be designed using OSTO MP8 standard specification for designing SMA and OSTO PP41. For preparing Marshall samples, 50 blows are given on both sides of the sample. The optimum binder content shall be determined by corresponding to the design air void content VA of 4.0% and minimum VMA of 17%. The minimum bitumen content for SMA mix is 6% by the weight of the mix. The results were tabulated in Table 4. Moisture susceptibility and indirect tensile strength, ITS. Moisture susceptibility is done in order to know the ability of SMA mix to resist the moisture damage. Around 6 samples were prepared, 3 samples were tested for conditioned and 3 were tested for controlled. The compaction of the specimen should be so that it should have air void 7AA plus or minus 0.5%. Here controlled samples were subjected to freeze-thaw cycle. Then specimens are tested for its. The TSR, tensile strength ratio, for SMA mix should be minimum 85%, IRC SP 79-2008. The indirect tensile strength, ITS, test was conducted as per ASTM D4123. Here, the specimens were loaded diametrically and the load at failure was noted down. The failure load obtained from the test was used to fix the stress level in the repeated fatigue load test. Repeated load fatigue test. Pavement distress of flexible pavements due to repeated application of heavy wheel loads is one of the major pavement failures. It is necessary to find the fatigue behavior of the bituminous mix under repeated dynamic load as in situ. The diametrical dynamic loading fatigue test is an indirect tensile test on a cylindrical specimen in which a repeating compressive load is applied along the vertical diametrical plane in a half sine wave pattern. The test is conducted for conventional SMA mix with optimum wrap material content and SMA with wrap material and bitumen modifier at 10%, 20%, 30%, and 40% of failure load which is obtained from its test. The apparatus is shown in below figure consists of LVDT, linear variable differential transducer, loading piston, loading frame, position controller, and data acquisition system with a loading rate capacity up to 5 tons. Load is applied over the specimen through 2 stainless steel plates using loading frame. When the specimen starts deforming, then horizontal and vertical deformation of the sample were measured using 2 sets of I.E4NO of LVDTs. The recording job of the applied load, deflection of both horizontal and vertical LVDTs for every cycle and the total number of repetitions before failure for each individual test was done by a data acquisition system. In the present study, the following test conditions were adopted such as loading frequency of 1 Hz, 1 cycle per second, failure deformation of 5 mm, pressure around 30 to 35 pascals. The following expressions from Kennedy, 1978, Gupta and Veeraraghavan, 2009, etc. were used for the computation of resilient modulus and initial tensile strain values from the experimental data. Resistance to rutting. Immersion wheel tracking test is carried out to examine the permanent deformation characteristics of SMA mix. One of the main reasons for premature failure of pavement is rut formation due to movement of heavy traffic loads. Immersion wheel tracking machine consists of loaded wheel of 5.6 kg/cm2 pressure and confined mold of dimension 60-10-20 cm in which specimen was placed and it was confined from all sides. In immersion wheel tracking machine, wheel is made to move back and forth on the specimen at the rate of 25 passes per minute, which exactly simulates the practical condition of vehicle's movement on pavement. Specimens were subjected 10,000 passes and rut depths at regular intervals were noted down. Graphs are plotted number of passes versus rut depth for 45 and 75 mm thickness specimens and were shown below. Conclusions. Laboratory tests have been carried out in order to determine the physical properties of natural aggregate, crumb rubber modified bitumen, CRMB, Bahus dust, and the results obtained were found to be well within the specified limits as per MORTH. From the Marshall stability test, optimum binder content for conventional SMA mix is found to be 6.3%. From Marshall test results it is observed that optimum wrap replacement percentage for SMA mix with wrap and WEO, i.e. 70%, is high compared to SMA mix using wrap without waste engine oil, i.e. 60%, at OBC 6.2%. Drain down test results obtained for conventional SMA mix using wrap without WEO, and SMA mix using wrap and WEO are found to be within the limit as per the MORTH. From the moisture susceptibility test results it is found that SMA mix with 70% wrap and 25% WEO shows higher TSR values compared to conventional SMA mix and SMA mix with 60% wrap without adding waste engine oil. From rutting test results it is observed that SMA mix using 70% wrap and 25% waste engine oil shows higher rut resisting property when compared to conventional SMA mix and SMA mix with 60% wrap without adding waste engine oil. From the fatigue test results, it is observed that SMA mix with 70% of wrap and 25% of waste engine oil shows more fatigue life value when compared to conventional SMA mix and SMA mix with 60% wrap without waste engine oil. From the cost analysis, it is observed that cost per cubic meter for SMA mix using wrap and WEO is less because of high percentage of wrap replacement when compared with conventional SMA mix and SMA mix with 60% wrap without waste engine oil. Hence by using wrap as an alternative material along with Rejuvenator makes the pavement sustainable, durable, and economical.